Hello. This video is a brief introduction to graphics processing units, GPUs, the backbone of AI. GPUs have transformed from niche graphics accelerators into the workhorses of modern artificial intelligence. NVIDIA, in particular, sits at the center of this revolution, providing both cutting-edge hardware and a rich software stack that together unleash unprecedented computing power. This overview will introduce NVIDIA's latest GPU hardware, like the H100 and the Grace Hopper Superchip, and key software components, CUDA, cuDNN, TensorRT, etc., explaining how they all fit together to accelerate AI. We'll also take a brief look at how NVIDIA became so pivotal in AI and how techniques like reinforcement learning are supported in NVIDIA ecosystem. Let's start with the differences between GPUs and CPUs. Modern GPUs differ from CPUs in their massively parallel architecture. While a CPU is designed for a wide range of sequential tasks, a GPU is optimized for throughput, crunching many operations in parallel. If a CPU is like a skilled chef preparing one order at a time, a GPU is like an army of cooks working on hundreds of orders simultaneously. This makes GPUs especially suited for the kinds of calculations AI workloads need. For example, training a neural network involves multiplying huge matrices of numbers, a task that can be split into thousands of smaller operations done in parallel. NVIDIA's GPUs, with thousands of simpler cores, can perform these operations much faster than a CPU with only a handful of powerful cores. In fact, researchers discovered that GPUs could speed up deep learning systems by about 100 times compared to CPUs around the early 2010s. NVIDIA recognized this potential early on and heavily invested in adapting GPUs for general computation and AI. Before GPU was even a term, there were graphics accelerator cards in the late 1980s and early 1990s. These weren't full GPUs yet, but they offloaded certain rendering tasks from the CPU. NVIDIA officially introduced the term GPU with the release of the GeForce 256 in August 1999. Originally, NVIDIA built GPUs for rendering graphics in video games. Drawing millions of pixels and vertices on screen is also a parallel task, which is why GPUs had so many cores in the first place. Around the mid-2000s, NVIDIA introduced CUDA, Compute Unified Device Architecture, a platform to program GPUs for general-purpose computing beyond graphics. This meant researchers could start using GPUs for scientific computing, and by the early 2010s, for machine learning. A landmark moment came in 2012 when a deep neural network called AlexNet, running on NVIDIA GPUs, smashed records in an image recognition contest, triggering the deep learning boom. As NVIDIA's CEO Jensen Huang described it, combining deep learning neural networks with NVIDIA GPUs was a pivotal moment that set off the modern AI era. Over the next decade, NVIDIA doubled down on AI. They improved each GPU generation with features for neural networks. For example, Tensor cores were introduced in 2017, Volta architecture, as special units just for the matrix math in AI. NVIDIA also built an extensive software stack, which we'll detail soon, so that AI researchers and developers had the tools to use GPUs easily. Today, most advanced AI models, from image classifiers to language models like GPT, have been trained on NVIDIA GPU-based systems. The company's hardware is so integral to AI that NVIDIA has been called the engine, or brain, of modern AI computing. In recent years, NVIDIA even achieved trillion-dollar market valuation, largely thanks to its central role in the AI boom. NVIDIA, along with Apple, Microsoft, Amazon, Alphabet, Google, Meta, Facebook, and Tesla, is among the 7 largest U.S. technology companies by market capitalization. NVIDIA H100 is the current top-of-the-line GPU for data centers, based on the Hopper architecture, named after computer pioneer Grace Hopper. Think of the H100 as a supercharged engine for AI computations. It's packed with over 80 billion transistors and thousands of cores, enabling it to perform trillions of operations per second on AI tasks. Compared to its predecessor, the NVIDIA A100 from the Ampere architecture, the H100 offers significant leaps in performance. For instance, it features fourth-generation tensor cores and a new transformer engine that can use lower precision, like FP8, dynamically to speed up training of large language models based on the transformer architecture. In practical terms, NVIDIA reports that an H100 can train gigantic models, think GPT-3 with 175 billion parameters, up to 4 times faster than an A100 could. It also massively improves inference speed, handling things like answering questions with an already trained language model much quicker, with NVIDIA claiming up to 30 times higher inference throughput on the largest models versus previous generation GPUs. What makes the H100 so powerful? Beyond sheer core count, it has huge on-chip memory and bandwidth, plus fast interconnects to link multiple H100s together. Important since big AI jobs often use many GPUs at once. An H100 in an optimized server can access memory and other GPUs at 900 GB per second via NVLink, a 7 times speedup over standard PCIe links. In short, H100 GPUs working in tandem can feed data to each other extremely fast, which is crucial in large AI clusters. These GPUs are the kind being deployed in AI supercomputers and cloud services. For example, large cloud providers might network 8 or 16 H100s per server, and then link hundreds of servers, to create a cluster capable of training state-of-the-art AI models. The H100 is truly designed for AI at scale, from its silicon to its networking. The NVIDIA Grace Hopper Superchip, GH200, pairs a CPU and a GPU on the same module, enabling extremely fast data sharing between them. In this design, the Grace CPU, an NVIDIA-designed 72-core ARM CPU, and the Hopper GPU, based on H100 architecture, sit side by side, connected by a special high-speed interface called NVLink C2C. This link provides 900 GB per second of bandwidth with a unified memory address space, meaning the CPU and GPU can access the same memory pool coherently. Why combine a CPU and GPU in one package? The Grace Hopper Superchip is built for giant-scale AI and HPC applications. The link between CPU and GPU delivers about 7 times faster communication than through a standard bus. In many big data or AI tasks, the CPU must prepare or manage data for the GPU. If the CPU and GPU are separate chips, data have to be copied across a relatively slow bus, creating a bottleneck. By unifying them with a coherent memory model, Grace Hopper removes that bottleneck. The CPU and GPU can work on shared data without cumbersome transfers. This novel solution effectively creates an AI superprocessor. Grace Hopper was a pioneering computer scientist and U.S. Navy Rear Admiral who played a foundational role in modern computing. She was instrumental in developing one of the first compilers and contributed to the creation of COBOL, one of the earliest high-level programming languages. Known for her visionary thinking and technical brilliance, she also famously coined the term debugging in the context of fixing computer glitches. NVIDIA named their Grace Hopper chips after her to honor her legacy in bridging hardware and software innovation. The chips themselves combine a Grace CPU, named after her, with the Hopper GPU, symbolizing the fusion of general-purpose and accelerated computing, much like how Grace Hopper bridged the gap between human language and machine code. The NVIDIA GH200 Grace Hopper Superchip specifically designed to accelerate the training and inference of LLMs. For instance, the GH200 NVL32 system, comprising 32 interconnected GH200 superchips, can train trillion parameter models over 1.7 times faster than previous systems. Recommendation systems also benefit from the GH200's high memory capacity and bandwidth. In performance comparisons, the GH200 NVL32 system demonstrated up to 5.8 times speedup over previous architectures in graph training tasks relevant to recommendation engines. Physics simulations, such as those used in climate modeling or particle physics, require immense computational power and memory bandwidth. The GH200's unified memory architecture and high-speed interconnects enable the simulation of complex physical systems with greater accuracy and speed. For example, the ALPS supercomputer at the Swiss National Supercomputing Center, powered by GH200 superchips, is facilitating advanced research in various scientific domains. Powerful hardware alone isn't enough. One of NVIDIA's biggest strengths is the software infrastructure that allows developers and researchers to actually use that hardware effectively. CUDA is the core of NVIDIA's GPU computing platform. Standing originally for Compute Unified Device Architecture, it's both a programming model and a set of tools, libraries that let developers harness the GPU for general computing. The CUDA toolkit includes a compiler, runtime libraries, and a suite of optimized math libraries. Essentially, CUDA provides a software layer that gives direct access to the GPU's parallel compute engines for running arbitrary code. So you can write C++, Python code that offloads work to the GPU. Training neural networks from scratch on GPUs is complex, so NVIDIA provides cuDNN, CUDA Deep Neural Network Library, a highly optimized library of deep learning primitives. These are basically the building blocks of neural nets. Things like convolution layers for image models, recurrent neural network functions, activation functions, pooling operations, etc. Major AI frameworks, including TensorFlow and PyTorch, all use cuDNN under the hood. Tensor Runtime, TensorRT, is useful for real-time applications or services at scale. It is an SDK and library for high-performance deep learning inference. Essentially, it makes AI models run extremely efficiently on NVIDIA GPUs. NVIDIA's hardware and software have clearly been instrumental in AI breakthroughs. It's often said that the resurgence of AI, deep learning, in the 2010s was software algorithm meets GPU hardware. By providing GPUs and the CUDA platform, NVIDIA enabled researchers to iterate faster, train bigger models, and achieve results that were previously impractical. From image recognition to speech synthesis to game-playing ICE, NVIDIA GPUs have been the de facto platform powering the compute-intensive training process. Many milestones are tied to NVIDIA. For instance, OpenAI's early work was done on GPU systems. Google's deep learning projects like cat recognition in 2012 also ran on GPU clusters. Even the development of self-driving car AI heavily leverages NVIDIA Drive GPUs. Beyond supervised learning tasks, NVIDIA also plays a role in reinforcement learning, RL, and other AI domains. Reinforcement learning is the branch of AI where agents learn by trial and error, receiving rewards for good decisions. It's used in applications like robotics, training robots to perform tasks, game-playing AI, and certain optimization problems. NVIDIA has applied and supported RL in a few interesting ways. For example, training physical robots through pure trial and error is slow and unsafe. So much of RL in robotics happens in simulation. NVIDIA developed Isaac Sim, a robotics simulation platform, and an RL framework called Isaac Gym, Isaac Lab to leverage GPUs for this purpose. In a fascinating crossover of AI and hardware, NVIDIA researchers have applied reinforcement learning to help design better chips. They treated certain circuit design problems as a game for an RL agent. The agent's goal is to arrange circuit components optimally. In one project, an RL approach was used to design arithmetic circuits that are smaller and faster than those made by traditional electronic design tools. NVIDIA GPU environment. The synergy of its state-of-the-art hardware and comprehensive software stack has been a driving force in turning ambitious AI ideas into reality. On the hardware side, GPUs like the H100 are pushing the boundaries of computation, enabling things like training trillion-parameter models and powering AI supercomputers. Innovations such as the Grace Hopper Superchip improves computing efficiency by integrating CPUs and GPUs. On the software side, NVIDIA libraries and tools, including CUDA, cuDNN, and TensorRT, make hardware accessible and integrate seamlessly, akin to building a rocket and providing the launchpad and controls. In essence, NVIDIA has become central to the AI revolution. Whether you are training a convolutional network to detect diseases from X-rays, running physics simulations for autonomous robots, or coding a new reinforcement learning algorithm, there's a good chance NVIDIA hardware and software will be your ally, accelerating your progress from idea to results. Thank you for watching. I hope this video helped highlight just how important GPUs are in the AI era. What are your thoughts? Feel free to share them in the comments.